Recording. Okay, so over to you, Mike.
Great, thanks, Brian. Thanks for the opportunity to talk this evening, and I'll go through the presentation in just a short while. So today I've been asked to give a brief background and understanding of where Rolls Royce SMR is with its development of the small modular reactor, and how much of the electricity can it supply for globally and for the particularly the UK. So, going to go over a bit of a background of Rolls Royce and Rolls Royce SMR, the demand for the product. So, design evolution, some key challenges, where we are up to with the design, next steps, and then questions and close at the end. And I'll take you through some of the key challenges as well that we've encountered, and I think the industry in general is encountering. So who am I? So I'm Mike Parrott. I'm the component design lead for pipework valves and the auxiliary components for the Rolls Royce SMR. I'm a fellow of the IMechE, which actually got confirmed today. So yesterday I would have been chartered. Today I've been given the nod for the fellowship, which has been a real achievement. So I started engineering at an engineering company in 2007 before I joined Rolls Royce Submarines in 2011. And then I worked in the design team supporting design developments, testing, manufacturing and service. But not only just spent time in the office, I was supporting the manufacturing facilities at Rainsway, and then also supporting the refurbishments down in Devonport as well. From there, I went on to support the next generation of nuclear attack submarines with the focus of new product development. And then I moved on from there in early 2020, just before I think it's 2 days before the pandemic hit, into Rolls Royce SMR from there. Okay, so I'll talk a little bit about the background, pedigree of Rolls Royce and Rolls Royce SMR. And please, like Brian said, if there's any questions, please put them in the chat, and I'll try and answer the best as I can at the end. So Rolls Royce has got a bit of a heritage across different areas of engineering, from civil aerospace, power systems, defence, civil nuclear, space exploration that they're looking into as well, and defence. So this is why, Rolls Royce believes it's in a really good position to support the market for civil-based reactors. We've been producing reactor cores and reactor pressure vessels, etc., for near on 60 years within the UK, and that technology is what we're looking to. Not necessarily that technology, but a technology similar to that for pressurized water reactors, develop that and put that into the UK market and the civil market. So using all that pedigree from fast manufacture, bulk manufacture, different systems, and bringing that all together to deploy SMRs. Okay. So what's the actual demand for these SMRs? So we know that across nuclear, there's a varied landscape. We've got large scale power stations that are being produced, Hinkley Point C, Sizewell C, etc. We've got micro reactors that have been generated, designed, developed across the industry, but they're not active in the market yet. And then we've got fusion in there as well, and all these have got strengths and weaknesses across the market. And I think what's been realised within the industry is that, one, there's a gap between that large scale and micro reactors, and that's where the SMRs come in. And if you went off the IAEA definition of a small modular reactor, Rolls Royce is just creeped outside of that megawatt of electricity. So we're quite high in that end game. But what we're trying to demonstrate here, and all this slide is really here to demonstrate, is that there's current technologies that are available. There's new technologies that are coming online, but the SMR fits in between those two gaps of utilizing a current technology that's out there and then productionizing essentially that SMR and that power station design. And like I say, both or all of these options have positives and negatives associated with them. And that's where we see the SMR sitting in the energy mix, along with turbines, wind turbines as well. Okay. So where do we think that the SMRs could help us? I think is what everybody's looking for. Is it just power generation, electricity? You know, we want to turn that kettle on and get that brew. Everybody, that's where typically people look for power stations to provide electricity. However, there is private utilization of these power stations that could be used for data centers, Amazon, Microsoft, Google, all that. They draw a huge amount of electricity from the grid, and so they are taking power that's generated by somebody else and putting it, utilizing it, so they're paying a premium for that electricity. So again, that's where the one solution that could be thermal power. At the end of the day, the reactor island and the nuclear propulsion section of that, or nuclear power section, is producing steam. So is there a way to utilize that steam for district heating across the globe, well, in the different areas, or can it be used for other things such as industry, for furnaces, etc.? We've also then got industrial power. So one of the things Rolls Royce has been looking at and has developed is a sustainable aviation fuel engine. So, and that's recently been flown from the UK to New York, and that was made with 100%, or that was flown on 100% sustainable aviation fuel. So again, all these things from a decarbonisation in the globe will need power. And if we're already producing electricity at the power station at that point of origin, and we're also producing heat at that source, there's no reason that can't be adapted to take off and automatically produce sustainable aviation fuels. There's also desalination as well that's required globally, hydrogen and other productions across the globe. And so we can utilize the power because they are smaller. They're still not small, but they're smaller. Can we utilize those for other solutions rather than just the generic large-scale nuclear, and where that cost of electricity will vary? So, what does that look like on a grid or different things? And as you can see here, you've got pipelines, different heavy industries. Everything needs electricity, apart from the solar energy, obviously. But where can we get that, and where can we use that? And these are some of the typical areas. We need electricity if we've got a factory to turn those machines to make products for the heavy industries, etc. So these are some of the grid connections, if you like, that could utilize SMRs, or could utilize, be topped up with solar farms and things like that. And then you've also got the wind turbines out in the distance there as well. So today, when we look at energy and demand and what that looks like, we know that we've got a retiring and aging fleet of nuclear power stations globally, and particularly in the UK. So even if we took the 473 plants across 32 countries, and we said that was 400 gigawatts of electricity, it's equivalent to about 750 SMRs. However, that's as it is today, and we're not saying that we're going to retire all that fleet and then just swap them out for SMRs. It wouldn't be economical, and we would have no electricity for a little while. But the production and the use of electricity is going to go up. So therefore, even if we had to meet a small increase in demand, that very quickly jumps up to the equivalents of about 1,600 SMRs. And again, if the global electricity demand went up by about 30% approximately, talking again 3 times that demand, so about 4.5, well, just under 5,000 SMRs. So if you roll that back, you've still got a huge amount of either new builds, large scale, or small modular reactors that are needed within the market. And that's why we understand as well that you're not just going to get the solution from one place, whether it's turbines, whether it's large scale nuclear, whether it's small modular reactors. There's going to have to be a combination to meet that energy demand from multiple solutions globally. And that's where one of the challenges, huge challenges, comes in to meet that demand. So where are we? What have we done? And how has the design evolved over the last few years? Like I say, I've been on the project since 2020, and it has evolved a lot, but it was also started prior to me joining. And what is the SMR? So on the left-hand image was a really early concept of the reactor and the steam generators and the pressurizer there. And then on the right-hand side is a more detailed version of what that is. These are the only 2 images really that I could look to share. There's quite a lot of pipe work running, supports for the steam generators, direct vessel injections, all those things that are really detailed and around in the integrated head package that I'll talk a little bit about as well in a minute. But what this is more typically trying to show is that we have evolved our design of the power station. The power station is continually evolving, and things are continually moving. The power station is a standard pressurized water reactor, and there is other technologies out there, and there is other ways of extracting or generating electricity out there as well. However, the reason we've picked a PWR for this SMR technology is because it's known, and there is novelty in the design that we have. However, we have picked it because it's a known entity, and therefore we know about PWRs. We've manufactured those for, like I say, for 60 odd years. So therefore we know our pedigree, and we know how to get to market quicker and how to support the UK's electricity requirements. We've got a 3-loop design, which is symmetrically laid out to support the core distributed flow through the core. We produce 470 megawatts of electricity approximately, and that again, like I say, is slightly above the IAEA's threshold that they've recently defined as a small modular reactor, which is about 300. So we've gone slightly above that. One question that typically comes out is why have we gone so high? Why have we gone to 470 and not straight to 300? And there's a couple of reasons. One, because that's how much power we can get out of this design, and we're used to designing things for small spaces and working on margins and understanding our design and how that works. But also, if you start high, you can always drift down due to tube wastage within the steam generators, etc. Whereas if you start lower, you're only going to drift lower and lower from that 300 mark. The SMR is designed for a 60-year life, which typically within the nuclear industry we understand that it gets extended, and we're used to that as well. But we are designing it for an initial life of 60 years. We are using a rich uranium dioxide fuel, so again typical fuel from within the industry. And the refuel period is currently sitting at 18 months. There's a stretch target that we're looking at for which is 24 months, but currently we're sitting at the 18-month mark, again to demonstrate we understand where we are in the market and where we are for maintenance. And we have a as part of Rolls Royce SMR, we have people on the as part of the board and investors, and one of those is a company called Constellations, who are helping us support the development of the SMR in terms of layout, in terms of system design, in terms of maintenance activities, as they are an operator within the US industry. So this is what the SMR used to look like. We used to call this the armadillo on the outside because of its shape, and then it's got a grass berm around the outside, and this berm was generated using the groundworks from below underneath the turbine hall and the reactor hall, and was taken out of there and then was put into this berm to create a security berm outside. This is what it used to look like, with the turbine island in the middle, cooling and reactor island at the front, and then the balancer plant at the back, and then this is the security berm on the outside. And then we had a bit of a reimagination and changed the design of the power station to look a little bit more technically, a little bit more aesthetically pleasing. Where we've got the offices at the front, and then there's this nice cover over the top of the power station to cover up what's underneath. However, I'll skip this one. Sorry. So what looks underneath? We have in here the first section here, which is the reactor island, or in the US, which they typically call the nuclear island. We have the turbine and turbine hall, and then out the back is the balancer plant, and also sorry, someone's just got the camera on. Out the back is the balancer plant section of the power station with all the supporting systems. But what you can see from this cross section here is that we have a containment vessel within the reactor island here, which is a metal containment boundary, and inside there sits all the reactor pressure vessel, control rods, pressurizer, steam generators, tanks, and the refueling pool, etc. And as you can see from the image, there's some module frame support in there, and there's quite a lot more detail that we've got in and around for the pipe routing, how would we build it, and things like that. At the front end and towards the back, you can see that a lot of the products are in modules or module frames. As you can see here, we've got some valves or some tanks inside module frames, and this is because of the way that we're looking to build this power station is using modules or skids and to speed up the assembly process of the power station. And in addition to that, we are also looking to put a skin over the top of the power station. So this large factory here will go on top of the power station itself, which is a large factory, but it'd be built up, taken down once the power station's been built and finalized, and before it goes critical. And the reason for that, there's a lot of work that would go into putting this factory up. However, the benefits that you will gain from having this factory are that you can work 365 days a year in the rain, in the wind, when it's dark, when it's snowing. You can still carry on with production and ensuring that the power station is built as close to its deadline as possible, because you can control the elements, you can control the light, you can control the temperature, you can make sure that somebody doesn't leave the back door open to when you're doing welding, those sorts of things. So this environment, we can control all of what happens within this power station just by having a skin on the outside of it. So all those critical tasks or heavy lifts can be done whilst they're in situ or within the factory itself. Another benefit we have is that this power station will be on a seismic bearing. as well. So that allows us to deploy the power station in multiple locations, whilst whether that be if you say Los Angeles, Turkey, UK, they've all got different seismic requirements throughout the world, and you'd be able to tune the base map to support the seismic graph in that location. We are basing our design on a single set of requirements at the moment. However, as the power station develops, you can then tune the map to support component justifications and extensions and localization, etc. If I skip back a bit. So when I talk about the factory and the factory being built, we have different parts of the power station that can be put in modules because it makes sense for them to be put in modules. And then there's products that there's no point in putting in modules because you're just putting a shell around something and taking up some space that doesn't need to have its space taken up. So there's some of the primary plant, so the steam generators, you'd put them in a big frame to help transportation, and you could also then use that frame to use it in the SMR itself for its location and supports, etc. But you wouldn't put the pipework in a frame because it's got bends all over and it's just a waste of space, and you need to connect everything at site. However, you've got then the modules, so you can put things in modules and skids, and similar to what we do, people do in the oil and gas industry, and connect those together. And then, but you'd also use that same philosophy, which is modules, skids, parts together, to improve that reliability and reduce the downtime, not just for mechanical products or electrical products, but also in the civils area. The more time you can take out of being at site and do away from the actual position of the SMR and then ship it in, you normally see a huge benefit of doing it in a factory in a controlled environment, and then deliver as much of it modularized as you can to site. So whether that be pouring the concrete and then fitting the rebar and then shipping those modules in, or tuning a map and then bringing that in, etc. It reduces that downtime at site, and if any problems occur. Another benefit is if we, with the modules, they can go through an initial test in a factory, again in an environment. You can do an electrical test on an actuator for a valve, as an example, to make sure it's receiving signal, make sure it's moving, make sure it's getting the right signals in and out. Do these cable lengths reach? Can we do an air test to make sure that it's initially holding pressure before you get to site and do its hydrostatic testing? So again, that has huge benefits, and what those benefits are in particular is about risk reduction, so that you're not getting to site and realizing that you've got an electrical fault. You may still have those, and you will still have those, but you're less likely to have as many at site, and you can do flow tests and things like that. It also creates jobs in prime locations where you've put those facilities to support the generation of those local areas. So what have been some of the key challenges that we've faced, still facing, and things like that? So we are doing parallel production, product design, and system development. So we're working alongside the system design teams. So we've got concurrent working to keep us at pace, but that's actually helped in understanding what our product ranges are, what do we need, when do we need them, and then it also allows us to understand risks and uncertainties within the design and the development, and have a real-time benefit of understanding what those exchanges of products are, where you change a valve from a gate valve to a glow valve and it changes the CV value. You can rerun those calculations very quickly together, rather than a report being issued saying this is the back pressure that we need for this system. We can impact that straight away. Getting the right engineering resource. It's no mystery that there's only so many engineers in the world, and getting the right type of resource into engineering or into Rolls Royce or into even the nuclear industry is really key, and it's also a challenge getting the right input in, but also ensuring that we're bringing people in that haven't got that background. And the reason for that is because you want different ways of working, you want different ways of problem solving. If you bring in the same people from the same industry all the time, you're going to get the same answer that you had last time. Whereas bringing people in from different industries, from whether it's from rail, whether it's from manufacturing, it could be from any other, oil and gas, bringing those in to see how those challenges can be fixed and resolved, really. So industry capacity for volume of products, for safety critical products in particular. So there's lots of manufacturing facilities globally, but there's only so many that can have that level of quality for safety critical components, whether that's enhanced non-destructive testing, whether that's understanding how you would do a defect tolerance assessment on a product, whether that's a different detailed stress assessment. There's only so many within the globe that you can reach out to. And they've also got a limited capacity because they're supporting other projects as well. So it's making sure that we understand what our resource demand is into them, capacity demand is into them, and when those times are, when do we need to get that volume from them, and when does that fit with us as a project? On the flip side of that is selecting standard products. So we want to ensure that we select as many standard products from the industry as possible. There's no point in me telling an actuator designer how to design an actuator when they know how to design an actuator. So therefore, we need to work with the industry as well to utilize as much of that capability and the capacity that they have as the design and their knowledge and their know-how, and incorporate that back into the design itself. So there's a real push-pull there with the industry of bringing people that know their products into the design itself, rather than us passing a spec out to the industry saying, yeah, you shall meet this, whereas a bit of openness and willingness to share has been fruitful so far. We've got some really good examples of where we've brought in companies that have products into the teams to share their thoughts and their approaches to product selection and things like that. So one of the other key challenges is the modularization itself, and it's not necessarily just the modularization, but it's proving to the industry and people around how can we do this? Can we do these modules? They are slightly different to a skid themselves. They are built transport frames. We need to move things around. We need to do connections. Will it increase the number of connections? Can you work inside these modules? Will everything fit? So we've actually built some just to prove it. So we've built some of those modules in the development centres at the MTC and AMRC as well, to support the development of these frames. And we've been running trials to make sure we understand how long does it take to move a frame from the ground up, just timing it, just to prove we understand our timings, how long a lift would take, what does that connections look like, what do the tolerances look like for the floor versus the frames, how would you make those frames, how long would it take to make a frame, all those things that are really critical to providing that pedigree and the backup to your planning, because that's what we essentially are going to use to develop that. Along that, like I said, we use the AMRC and the MTC to support that. But we've also started making some things out in the general supply chain as well, to demonstrate that the supply chain capability is out there as well, to ensure that we're not just doing this in a single factory, and therefore it can't be repeated. And and we need to be able to deploy this potentially globally as well. So understanding those pitfalls, what are those niche products? What are those niche manufacturing techniques? What is niche about these things? We need to know, so we can either design it out, or we can work out how to deploy that globally as well. So the next steps, as you can see here, it's an empty module frame. There's a bit of, there's some railings around the outside, and there's some stairs. However, we've actually started developing and they've been working on making and filling these modules with products to demonstrate that all the products fit. To work out, we've been doing some augmented reality work as well, so we can fold that into there as well. Look at the connection methods, space for welding, using TWI and other organisations as well to support the real demonstration that this does work. Another key challenge, completely beside manufacturing and actually making these things, is alignment of regulatory processes. So we're currently going through the UK generic design assessment with UNR. This provides a really good base for our design and global confidence in the product and the SMR itself. And we are delivering a whole SMR solution. I'm not here to say what other people are doing and things like that, but we are here to provide a whole SMR solution from the concrete all the way to the power grid. But every country has a slightly different regulatory process or different regulatory requirements. So the challenge is aligning all those different pieces of the puzzle globally as well, and satisfying those different regulators. You've got the US NRC out in the US, for example, and there's different out in Sweden and things like that. However, this has been recognised by the IAEA, and they have got a forum that is there already now to bring in all the different regulators to try and iron this out best, of saying how can we move things from one country to another easier and things like that, so that if we've been through that regulatory process and it's been approved, how can we make the industry or help the industry move at a faster pace, whilst ensuring safe operation and safe deployment of the power stations themselves. So where are we up to? So alongside maturing the design layout, we are progressing through the GDA process. We will be completing all 3 stages of the GDA process. A few years back, it changed, I think, from a 4-stage process to a 3-stage process. We have completed step 1. We are nearing the end of GDA step 2. So that's been quite some push to get us there. We've produced over 1,000 documents to support that GDA step 2, and then we'll be stepping straight into GDA step 3, which is the final stage of the GDA. It's all a tough process, and the working with the regulator has been really, really good to get to where we are as well today. Next steps, I think I've touched on them a little bit throughout. So completing the GDA step 2 process, completion of the GDA step 3 process. We'll be placing long lead orders, hopefully soon. Completing the modular demonstrator, and then looking to secure orders in the UK and abroad for the SMR design itself. Apologies for whizzing through a few of those bits, but that is the final slide. Thank you, Brian.
Thank you very much, Mike. That's really interesting. We do have already quite a few questions in the chat box. If you're happy enough, I'll go through the questions and you can provide the answer. So the first question was, what would you say is the level of design maturity at the moment? Your talk suggested that there's still significant changes to come.
That's a really good one. So we're actually quite far through the design. We are quite mature, and with any design process, things always get tweaked and changed. But we're actually quite mature in a lot of places, and it's more. We call them changes. We call them design changes, and it's because we put them through a change control process. We do reference design points quite often throughout the year to ensure that we're under the change control process. But they're probably more minor adjustments than they are evolutionary adjustments to the design itself. So we are set on number of steam generators, for example, out where they're positioned and things like that. So we are quite well set in the design, and we have to be to get through and to support the regulatory questioning and demonstrating our viability of a product.
Okay, next question was maintenance needs. Are they similar to those of existing reactors?
Oh, that is so typically yes. So we are looking to use as much digital experience that we have from the aero side and implementing that into the SMR itself. So we will be increasing some maintenance, not increasing the maintenance periods, but increasing the data that we see from certain products, and probably introducing additional sensors and data that's coming back so that we understand, so we can do more predictive maintenance with the products as well. So we are looking to reduce our downtime for our maintenance periods. Typically, we've estimated it in the down scope of about 18 days, which is typical for the nuclear industry. However, as always, and what you should be doing is looking to improve on that, and we are looking to reduce that significantly down as well, to based on data. And we're part of EPRI. We've signed up to EPRI, so we get to utilize the data that's provided by EPRI and approved by USNRC as an example to support our justifications in how that maintenance would be looked to deployed, where typically problems have occurred, and where they could, how can we look to design that out as an example as well.
Does that mean more condition monitoring than would be typical on existing?
Yeah, a bit more condition monitoring. Years back on a lot of the motorized operated valves and the air operated valves, condition monitoring wasn't as high as it has been. Yeah. So so we've developed. That's why we've been working with EPRI as well to understand that, and that's where people were getting a lot of failures across the industry based on not doing enough condition monitoring. So that's why we're designing our plant now with condition monitoring in it, so that we can reduce our outage times and increase our availability at the power station as well. So, if it's not operating or there's a maintenance issue, there's that incurs costs. So, and we want to run safe and safe power stations. So therefore, we need to understand what the power station is doing, and by doing that, you can do that through monitoring.
Okay, thank you. What is the percentage of modularization?
Wow, that's what is the percentage of modularization? Well, it's part of the policy so it's probably the other way around. It's more of a what isn't modularized is the way that we've approached it. So we have in the policies that we work to, we have standardization as a key factor to work to. We have modularization, government and regulatory approvals, etc. So more of the power station is modularized than not. It would be hard to put a figure on it, but it's well up there. It'd be over 50% of the power station.
Okay, thank you. How much commonality with PWR3?
PWR3, I'm going to assume that you're talking about submarine in that.
I assume that was the case as well.
Yeah, not similar, because it's not a that is a different design, and it's a different design for other security and other reasons. So it's a PWR that has got an operational philosophy that is different to PWR2 for a start. So therefore, that's probably all I'd want to stay on
Okay,
that.
thank you. The next question is actually to both of us. What connection does the SMR have to Oxford? Are there collaborators, suppliers, employment opportunities here? Can I answer first?
Absolutely.
If you're asking why we laid this talk on, it's because there are an enormous number of engineers within this area that are interested in nuclear, with Harwell and Hallam and some of the independent fusion work and other things that are going on here. And you can see from the enormous, I mean, it's the highest attendance we've had for a meeting for a very long time, that it's a popular topic for this area. I'll ask you, are there any direct connections now?
There haven't been, but we are looking to establish. Rolls Royce is a sovereign capability that we're designing. We're looking not just to reach out in one particular area. We're looking to reach out to the whole UK. So, these collaborations and these discussions, we want to do more of them, and we want to get these out into the UK, because it's a huge benefit to the UK and to the UK market in particular.
Okay, and I think the next question is perhaps prompted by that, is what type of work in engineering consultancy companies can expect on the project in the next 5 to 10 years? In other words, are you going to be looking outside Rolls Royce for consultancy type input?
Yeah, so we've got around 600 employees at the moment within Rolls Royce SMR. Some of those are supported by consultancy companies as well, for particular areas of the power station design. We are looking to increase the number of employees within SMRs. We've got job outputs out for all different component design engineers, product engineers, manufacturing engineers, verification engineers. So there's lots of different roles already, just even within Rolls Royce. And and as I said, as part of the problem that the challenge that we have within the industry is we need more people, and therefore we will be looking for expertise within the UK to support that, whether that's through a consultancy or through a permanent job role as well.
Okay, could you explain the 3 GDA steps? What are the requirements for each of those steps?
So each of the steps, you're there to demonstrate, do you understand the philosophies of the power station and its waste systems, how you'd manage the fuel, how you would ensure safe operation of the power station. And as you go from 1 to 2 to 3, you have to demonstrate the maturity of the design, and the evidence that you need to provide is greater. You need to prove how the systems work, how not just how the components sit on the shelf or are incorporated in there. It's all the philosophies of how you're going to operate. It's philosophies how you would maintain, philosophies of system design, and some of those system design for decay heat removal, or emergency core cooling as a function rather than as a system. So how does it work from a function, and then what systems are used to generate that function? And then so there's that, and then you have to demonstrate that the components that you have put in to achieve that function and achieve that system design are available, that they work, and then you've got to demonstrate again what verification and validation methods have been used to demonstrate that those are available. As an example, as a verification and validation activity on a valve, for example, we're designing an ASME plant. We're designing it to the ASME design code, and as part of that design code, we have to do qualification testing of certain valves that need to either safely support safe shutdown of the power station or safe operation of the shutdown. One of those valves, as an example, is the main steam isolation valve, and that we have to therefore put through a qualification test, and that qualification test is shaker test, full flow, etc. So we have to go from very detailed how you're going to do the design and qualification of that single product all the way up to the end. and demonstrate that we understand all our philosophies with giving examples and providing that evidence and that golden thread from generate power to verify test results all the way through to the regulator to show that we understand our processes and products and how we're going to meet those safety demands that we've set.
Okay, thank you. It might be early, but is there any strategy work being done on how nuclear waste will be managed that is coming out of the SMRs?
Yeah, so waste is is always a challenge, and we have to look at waste as part of the regulatory process, how we process waste, what we do with waste, what we do with it after, and where is it going to get. So yeah, there's the strategies that's been developed and working on within the company for waste itself.
Okay, and then in the light of NuScale in the US declaring the cancellation of their SMR reactor project in Utah, where the price per megawatt increased 53%, what market price is Rolls Royce currently targeting, and how confident are you that this can be met?
I've got a slide somewhere. So I'm just trying to convert it from dollars to pounds. I'd say we've already aimed high on that unit into where they're currently looking, and probably slightly above that as a target, because we understand that there's going to be economies of scale and where we're going to end up in the end. And what was this? And so I think there's other factors, not just necessarily linked to the cost of megawatt per hour. However, their modules or their power station was a 77 megawatt of electricity per unit, and then they were going to increase the power output by having multiple units in their modular design.
Okay.
So where we have a larger footprint, we are able to control our production, and that's again why we've gone high. So if you go to a certain scale and you get to a certain level, your economies of scale, you've got that benefit. So you're not going too far, that you're too close to the large power scales and power stations, but you're not too low down in that market as well, that you're going to cause yourself a problem with being not cost competitive against your megawatt of electricity. So therefore, by where we are, we know that the market, we've got more space to maneuver around that cost of electricity.
Okay. Any info on fuel assemblies? Is refueling done via a shutdown or while in operation? I guess that's an easy one.
Yeah, we've done during shutdown, similar to a normal power station.
Yeah. What are the anticipated hazards during operation, and what will be the mitigating measures? I mean, that's how long is a piece of string?
What are the potential hazards? Operators, human intervention. There's. I think in the nuclear industry, there's in any industry, there's always a hazards, and we're designing in even manual handling and how we operate and how we maintain our products. That's been put in now. So we have we've been developing that into the power station again. So we're trying to take lessons learned from other places as well and design that into the power station. So we're trying to minimize the number of hazards, but there's lots of hazards when working with mechanical equipment, unfortunately.
Yeah. Will all modules be road transportable? I guess the answer is they're manufactured on site. So,
well, they're manufacturing a facility and then they're transported to the SMR site. So they don't have to be at the SMR site. They could be somewhere else and then transported in. So typically, yes, they are road transportable. We design the modules in a couple of different sizes so that you can do like a stacking effect if the product's bigger than a single module. And that's where we would get the an increased benefit is that you can do multiple modules off-site and transport multiple modules together and stack them. There is a limit, and we've done studies globally to look at what that transport limits would look like, not just for the UK, but places. As an example, for the Czech Republic, it's quite well known that I think Tufan has made that quite, out there, that we are looking with we've got MOU signed with the Czech Republic, and we've looked at their transport limits and what they would need, and that's impacted our design. So again, we understand how we would transport things, whether it be via rail or by road, and we have sizes for normal loads or normal sizes, and then we have abnormal sizes as well. So we understand what they are.
Okay. What will happen at the end of life? Will they be fully dismantled? Will they, or can the reactor itself be replaced?
It's essentially going to be decommissioned. At the moment, the plan would be to be decommissioned similar to any other power station. Whether the turbine can keep going, as an example, and you need to replace the core and things like that. It's whether it becomes a scale of economics more than anything else, really.
Out of order, there's a linked question: is how much have you looked at decommissioning in terms of the design of the modules?
So that's what we have to look at decommissioning as part of the regulatory process. We have to ensure that we understand how we can decommission these products and what's the waste of those products as well. So we have to look now at decommissioning, just to understand what that decommissioning would look like, albeit not as detailed as producing a plan of saying you would unbolt this and you would therefore remove this, and then this is the amount of waste and so on and so forth. But we have to. It's part of our consideration now of minimising waste for the power station itself afterwards. So from one product to another, it was 5 times the size of something else, so therefore we'd go for the small one potentially, just to reduce the waste that when we come to decommissioning as well.
Okay. Who'll operate the SMRs day to day?
There's a couple of options. So we could operate them. That's one thing. We can sell them to somebody else, and then they can operate them. So, like I said, in the Czech Republic, there's Czechs who could operate them themselves. And we've got Constellation as part of they're an investor. They would be there to train up or even operate the power stations as well. So there's many different opportunities in there, and that's still up for grabs, I think, at the moment. And I'd say it depends on the local, what's agreed as part of the contracts and arrangements.
Okay. What percentage of the components modules will be sourced from the UK? And I guess the question really is, does the UK manufacturing have the capability for some of the key components?
Some of the key components, yes, we can make in the UK. Not all components can be made in the UK, but when we talk about manufacturing in the UK, we will be looking and we will be getting stuff from the UK. That's part of what we're doing here. We are trying to revive some of the UK industry. We are trying to support the UK industry, and where there is capability within the UK industry, we'll probably look to utilise that as much as possible, where it's practical as well. Some products can be made in the UK, but they might not have the pedigree that's required to support them. And that could be for the first of, or it could be the second of and third and fourth. So we will get the product to market first, and then we can deploy strategies, and depends on the UK government how much they want localization and things like that, because it's all down to cost, and there's many different factors as well to that. So if there's other products, and say one was 50 times more expensive to get it from the UK than somewhere else, if that economy of scale is okay because of X, Y, and Z, then that's probably where you'd start to look of is it worth? Could you get it from the UK? Whereas if it was the same cost, pedigree, etc., then there's no reason why you couldn't do.
Yep. During core shutdown for maintenance, is there any secondary generation to ensure local load requirements can be continuously met? If not, do you need a pair of SMRs for firm supply?
First answer is yes. You need. So we're saying that the power station or the SMR would give you 95% availability. So a pair of SMRs would generate 100% availability, and that's where, if we produce excessive amounts of electricity for that area, you've got then other grid connections, data centers, like I said, desalination, and that's where the power station becomes more adaptable in terms of you can use it for other things as well as just generating electricity. So you can use one for producing, say, sustainable aviation fuel and data centers, etc. And then say that went down, you could swap them over, etc.
Okay, and which component, equipment in the reactor or other buildings has the longest lead time? I guess this is how long is it going to take to build, which seems to be a major problem with current projects.
We started a while ago with this project, so I'd say reactor pressure vessels are probably the longest pole in the tent for some of this kit. From a safety critical and product, and we understand how to make those. We've made them before, so we're very well versed with understanding that sort of product.
Okay, thank you. That is the last of the questions in the chat, and well, great presentation, Mike. Well done with your handling of the questions. And I would echo that. I think we'll bring things to a close at that. Mike, thank you very much. I think that was a really interesting presentation. I certainly learned quite a bit. And I think you've got you've made some interesting progress there, but I think you've still got quite a few challenges there. I guess if people look on the Rolls Royce SMR website in terms of job opportunities and things like that.
Absolutely, yeah. There's lots of jobs. I'd love to show more detail. We are really well advanced in certain areas. It's just for commercial reasons. I can't share anymore. Otherwise, I think people would be shocked at actually how far we are through the design process and product selection and things like that. So unfortunately, I've probably shown you data from that's old in terms of it's like a year or two old. You know, we're really advancing really quickly. But yeah, I appreciate the time to talk to everybody and present where we are, and hopefully it was interesting.
Okay, well, thank you very much indeed. There's a lot of thank yous coming up on the chat box, and I think the range of questions shows the level of interest. So thank you. Thanks everyone for attending, and hopefully we'll see you at a future Oxford event, and end by congratulating you on becoming a fellow. I did say to you that this would look good on your application, and it wasn't necessary.
Appreciate it. Thanks, Brian.
Right. Cheers, everyone.
Thank you. Cheers. Take care.